Okay, remote student, can you see my screen? Can you see my slide?
Yes.
Okay.
Yes. Yeah.
All right, thank you. If there is anything, some problem, just speak up. Sometimes I need to fix that immediately. Okay, so this is so this quarter I select a bunch of topics which I think is very critical for you to understand, and this principle can be applied to a lot of different situations. And today I'm going to talk about another such topic, is really talk about interference, about synchronization and priority scheduling. So synchronization is important. Like last time we talked about, you actually guarantee the consistency and things like that. So let's actually first take a look.
Professor?
Yeah.
Sorry, we are seeing the presenting view.
Hold on one second. So let me see if I can do this. Let me share the full screen. Can you see the screen right now?
Yes.
Okay, all right. So this is, you just missed this slide. This is the previous slide. I was talking about the concept, priority inversion. So what do I mean by priority inversion? It's a interference between two mechanisms using any kind of system that will handle concurrent activity. So the first one is a real-time priority scheduling. So we have a bunch of tasks we need to handle with a limited amount of CPU resources. And therefore, for any type of real-time system, we need to settle down on something we call priority. So we actually need to assign priority to each of the tasks, or sometimes each of the threads. So it will be executed according to their deadline requirement, for example. Okay, that's called real-time scheduling, or sometimes we call priority-based real-time scheduling. The second mechanism, as I list here, is called mutual exclusion. So mutual exclusion is, you can consider this as a lock. Sometimes we use another form, Semaphore. So mutual exclusion essentially designates a period of time or a segment of code, and such that nobody else can get into that particular section. So you can think about is I lock. When I get into that critical section, then I unlock. So when I lock, nobody else can go in. That's actually the concept of mutual exclusion. It's the idea is try to protect the integrity about what we would like to do. I mean, in some sense, mutual exclusion is so useful, but it causes problems. Like the whole design of GFS, they try to reduce the amount of mutual exclusion as short as possible, because any kind of lock that's actually for extended period of time, that means your system will not be able to handle too many things. You have to wait until this particular mutual exclusion condition was removed before we can make progress. That's why in GFS, they don't want any kind of, when they handle concurrent write, they don't want to lock it. They actually relax the consistency condition, and such that the result difference will be handled by the application lead, for example. But typically in real-time system, especially in some of the control that we need to handle, like a robot, that we still unavoidably using mutual exclusion. But usually we have a way to make sure the mutual exclusion is really short. Really short means just a few instruction or maybe less than 20 instruction. So essentially, the period of mutual exclusion is extremely short, such that no problem, we can actually take care of that. Just whatever condition that's blocking by the mutual exclusion will be removed in about 20 instructions. Okay, no problem. That's that. Okay, so we talk about this picture, just to let you know. On the left of the slide, that's the typical notation I will represent critical section or mutual exclusion. So you see that before I enter mutual exclusion, I will try to do a lock. And when I exit, I'm going to do unlock. Okay, that's the, and then on the right is a typical scenario to do priority scheduling. That this is the kernel design, for example, for FreeBSD. So FreeBSD has 64 different priority class. And the thing is that each of the threads is being assigned a priority from 0 all the way to 255. And so whenever a thread is being put into a ready queue, it's actually looking at the assigned priority to decide which of the 64 queue that it needs to go in. So the scheduler, when they do context switching, it basically take a look at the 64-bit. By the way, why 64-bit? Because at that time, we're actually primarily using 64-bit computer. So we have a 64-bit represent which of the bits, that's 1. That means they have some task that's actually need to be executed. So essentially, they say the first bit they encounter, that's the higher priority queue. That means, okay, I'm going to serve that queue only first before I serve others. So that's basically a priority scheduling, is that we place the ready job into one of the priority queue, and we always actually serve the highest priority first before we actually get down to the bottom. Okay, so that's real-time scheduling on the right, and then mutual exclusion. Okay, I'm going to use some example to start to describe or illustrate the issue of priority inversion. So in this scenario, I have 3 threads. I have 3 threads. If you are unfamiliar with the concept of thread, you can think about just 3 programs or 3 processes. Of course, there is a special things that differentiate threads and the process. Okay, at this moment, I'm not going to worry about the difference. I mean, the difference is threads might share memory, process won't, essentially. So in the picture, I actually have 2 kinds of letter. One is L, one is R. So L stands for local CPU burst, means that this is non-critical section activity. So R is resource, means that they are critical section activity. So in this case, that we actually have RX. So I have a different kind of critical section. In fact, in a general system, for example, a typical operating system has probably at least 2,000 different kind of mutual exclusion in the kernel, at least 2,000. There were so many things you need to do mutual exclusion in a typical kernel. The number probably can grow. Of course, when the number grows, you can imagine the complexity of to understand and program the kernel sometimes is a challenge as well. But anyway, in this example, I said there was a 1 critical section called RX, a particular one. And that critical section was shared between thread number 1 and thread number 3. So I have 3 threads. Thread number 2 doesn't need any mutual exclusion. It's only have a non-mutual exclusion activity. Okay, 3 threads. Okay. So what is a typical thread looks like is basically you do your local work, that's L, and then you actually do a lock. Or the other way, by the way, if you learn operating system at undergraduate, sometimes we use the term semaphore. And in semaphore, just to let you know, semaphore has a binary semaphore. Binary semaphore is essentially equivalent to lock and unlock or mutual exclusion. But there is a general semaphore. General semaphore means that it's not just a lock, 1 mutual exclusion, it has multiple units. So typically, lock unlock means that you have only one person can get into the mutual exclusion. But what happened? I allow 5 people to go in the mutual exclusion. So that's become what we call the concept of general semaphore. The same concept you learn from this class can be extended to general semaphore, but from now on, I'm only going to worry about binary semaphore. Means that at most one thread is allowed to enter that critical section. Okay. Right, so basically you wait for that semaphore, then you go in to actually enjoy your mutual exclusion. After you're done, you do signal. So in semaphore, we use the term wait and signal. Wait means you want to enter. Signal means you're done. So you signal other people to let other people to be able to get in. You release the semaphore. And then after that, you're done with the work. Okay, so now let's actually look at the scheduling. Okay, the scheduling looks like this. Assuming the thread number 3 come in first. Thread number 3. Remember, this is a real-time. Oh, I forgot one thing. Thread number 1, 2, 3. The number 1, 2, 3 represent their priority. So thread number 1 has the highest priority. Thread number 2 is a median, and thread number 3 has the lowest priority. Okay, just for this example, 1, 2, 3. So assuming the system thread number 3 come in, it's the lowest priority. So you come in, and right after you enter the semaphore, enter the R. So he's actually holding the R, and thread number 1 come in. So when thread number 1 come in, this is called preemption. Because why? Thread number 1 has a higher priority than thread number 3. So that's why you will see the blue line means that it's a preemption. I actually kick thread number 3 out, and then I can actually do the work I want to do. But at some point, thread number 1 reached the point he wants to get into RX, the mutual exclusion. It cannot. Why? Because thread number 3 hold it. So this is called blocking and waiting. So now at this moment, thread number 1 is no longer ready. It's actually being moved by the operating system to a blocking or whatever waiting queue for the signal for the signal of the semaphore. Then it can continue. So you will see this kind of scenario. So after thread number 3 finish, it release the semaphore. Immediately now we switch back, because when the signal of the mutual exclusion is available, that will notify the kernel, and the kernel immediately put thread number 1 into ready queue again. Whenever it put the ready queue, it's a higher priority. It will be served, it will done. After it's done, then it come back to thread number 3. So it's finished. Okay, so this is just a simple interaction between real-time scheduling and mutual exclusion. Okay, any question about this diagram? Yes, please.
In the previous slide where you showed 256 bits, the one. So can you explain what do you mean by 64 and 256? I didn't understand.
Okay, so this is purely implementation issue. So in any Unix operating system, at least for a long time, they have 256 different level of priority. Okay, so this is a FreeBSD kernel's implementation. They decide to implement the concept priority scheduling using 64 different queues. So in other words, priority 0, 1, 2, 3 is actually going to assign to the first queue. And then 4, 5, 6, 7. So it's basically each 4 level matched to each class. It's purely implementation. I could have an implement 256 queue, right? But I guess it's because of this, it's a 64-bit computer at the time it was designed. So that's why they use 64-bit.
So inside the 64-bit, each 4 bits means 1 priority.
Say that again.
Inside the 64-bit, you can divide this into 4 bits. That means that you can have the
No. Each bit represents 4 priority. So I have a 64-bit, right? Each bit represents 4 priority. So that's why 64 different classes, that's actually cover all 256. So in other words, what I'm saying that if you're in this system, If you're priority number 2 and priority number 3, it doesn't matter. In this implementation, they will be treated as the same. Yeah, it's using priority class in this particular scenario. Yeah.
So priority, go back to the slide. So priority doesn't necessarily like mean that you have priority in those like race conditions are, but specifically in the scenarios where it's just L.
Yeah, priority only affect L. It won't affect R because you already, okay, so here we're assuming we're doing preemptive scheduling. Preemptive scheduling means that you can be throughout anytime. That's preemptive scheduling. But preemption won't be able to touch the critical section. So when you're inside the critical section, you cannot be preempt to go out of the critical section. You have to wait until it finishes. That's what it says. Okay. And of course, there's a whole class of non-preemptive scheduling, which is, for example, Unix system call is usually being implemented as a non-preemptive scheduling, means that once you get into the kernel, you have to go out. And then early 2000, they start to introduce a concept called fully preemptive kernel in the kernel. So it means that they actually do a lot of things to make sure that even the kernel can be preempted. Yeah. Now this day, most of the kernel are fully preemptive. Yeah. Okay. Any other question? Just make sure this slide is you understand everything, so we can move on. This thing's getting interesting after that. Okay, so now we haven't talked about the middle thread. So assuming I'm actually asking over here at this moment, but what happened is that if you remember, where's the middle thread? Oh, I don't have that picture. Anyway, that's okay. I'm going to use this one. So the middle thread actually come in around this time. The middle thread, remember the middle thread doesn't have any mutual exclusion, it's purely L. So it's actually coming at this time. So when you're blocked, when priority 1 get blocked, according to the diagram I showed you, now I have 2 processes in the ready queue. One is thread number 2, one is thread number 3. So which thread should I execute? Thread number 2 or thread number 3? Thread number 2, right? So this is actually what's going to happen. The thread number 2 is coming in because thread number 2 is higher than thread number 3. So you essentially preempt thread number 3 to do anything. And now, because I'm the king now, thread number 1 is not ready. I'm the only one is available. So I actually got to execute. And then for a long time, and then until I finish. And now thread number 3 got to execute. And now thread number 1 final. So essentially, this is a very important picture because now thread number 1 get indirectly blocked by thread number 2, which has a lower priority. So that's called priority inversion. Because if I'm only get blocked by mutual exclusion, that's fine. It's mutual exclusion is supposed to be short. But if I'm blocked by thread number 2, I actually don't know how much time it will take. It depends, right, on the activity. And so this could be really bad if you have a lot of thread number 2. If you have a lot of them, you just keep blocking it, and okay, your high priority get into the trouble. So this is a problem that we actually see in the actually, do I have this slide? Let me actually take a look. We actually know the problem of priority inversion. We actually have the solution before this happened in 1997. So in 1997, there is a Pathfinder on Mars. This is actually by NASA. And they actually have 3 tasks. the high priority task, which is actually try to get the data from the shared memory, but they have a median task is doing the communication with the NASA base station in Florida, Houston, I forgot, never pay attention to the detail. But lower priority is essentially collecting all the data, the sensor, and then the high priority task put into the shared memory. So we have 3 tasks. So as you can imagine, that the highest priority thread, it's very hard to get into anything. So because of what? The communication, there is a lot of communication happening in the median task, and the highest priority task is just not functioning. So this is really the first noticeable incidents about priority inversion in real case. It's not even on Earth, it's actually on Mars. So just make a long story short, what they have is the operating system, I forgot what it is, I think it's a VxWorks. It's actually already implement a solution I'm going to talk about called priority inheritance, but it never turned on. So it's a mechanism already implemented in the Pathfinder, but the feature never turned on. So to make a long story short, they eventually use remote login to actually turn on that bit. And so the Pathfinder has that priority inheritance feature, and such that everything go back to normal, and then the higher priority task will be able to function correctly. Okay, just make a story. So, so what we want to do, so this is the problem, and how do we resolve it? So this is a concept called priority inheritance. So priority inheritance means that at the time when a lower priority task is blocking. Yeah, a lower priority task is blocking a higher priority task because of mutual exclusion. Then basically the lower priority task priority need to be bumped up to the same as the higher priority task that's actually being blocked. Okay, so that's called priority inheritance. It's very simple, right? You just go down there and then go there, and now you can see that it solved the problem I showed you earlier, that the priority thread number 2 no longer can come in, because now thread number 3 has the appropriate priority, and I will actually return the priority back to the normal when the blocking condition is done. So you can see that I actually release it. Now after thread number 1 is done, now thread number 2, and finally thread number 3. Thread number 3 actually still finished the last. It doesn't cheat or anything, but it's just doing things like that. Okay. So this is first time talk about a very interesting paper. The paper I sent you is the original paper by Priority Inheritance Protocol, published in 1990 on this case. Okay. All right. So hopefully you understand. Let me actually explain a little bit about what's going on in the basic priority inheritance protocol. So the basic priority inheritance protocol means that I actually have for each of the mutex, which is a mutual exclusion, has a waiting queue. That's actually for every task want to enter this particular semaphore. Okay, so we have a queue, looks like this. By the way, that queue is not a FIFO queue, it's a priority queue. So when you enter the task range according to their, now I'm going to use the word very carefully, not the original priority, but the effective priority. So now you see that the system is start getting complicated because a thread's priority might change. My priority is low, but as long as I have a resource and then somebody else is waiting for me, my priority get bumped up. Okay, so that is actually going to be in that queue. So essentially priority inheritance is that the highest priority of every thread in that priority queue is going to push to the current holding thread if that thread has a lower priority. Okay, so that's how it implements. Has a queue, And whenever there is a threat coming in, I will update. And the thing is that sometimes it might be even more interesting that I might holding multiple queue. I might holding multiple mutual exclusion. So therefore, my effective priority is going to be highest among all of the queue I'm in. Okay, and there's another thing called transitive priority. It looks like this. So transitive priority means that the pink is holding for yellow, and the yellow is waiting for the first M2, the mutual exclusion. But now there is another priority, high priority, even higher priority threat is trying to get into M1. So this is called transitive priority because any dynamics into the queue on the far right is going to change the priority of that yellow. And change the yellow potentially actually change the pink. So essentially, I'm actually telling you not just the principle about transitive priority, but it's a software complexity. You can imagine if you want to implement this, you have to actually track anytime something go in, it's going to trigger potentially a chain of priority change across multiple mutex that's actually used by your system. I said earlier, the kernel, when I did the programming, it's about 2,000 mutex in there. And the thing is that this 2,000 can be actually related in a way that's actually quite hard to manage. Okay. So this is a basic priority inheritance protocol. I just have a way to continuously monitor the demand and supply of mutual exclusion. And I manage their priority and such that I will make sure the one that's holding mutual exclusion or semaphore is actually receiving a higher effective priority, and then it will release whenever something changes. So that's basic inheritance, sorry, priority inheritance protocol. Any question about, maybe I just show this picture. It's probably the most complicated picture. Any question about basic priority inheritance protocol? Okay, if there is no question, what could be the problem or disadvantage of this basic priority inheritance protocol? What could be the possible problem?
Every time there is a dependency, there can be a lot of system work you have to change the priority.
Right, that's one issue, right? One important issue. There is a lot of dependency relationship I need to track. It's always an issue for a lot of this kind of system. That's definitely one of the issues. You read the paper. It talks about transitive priority inheritance is something which they eventually manage to avoid. And we don't have to worry about that. Okay, it's a software implementation issue. Okay, there are two main problems with this basic priority inheritance protocol. Number one, I don't know whether this is intention or unintention. I mean, the inventor of priority sealing protocol or priority inheritance protocol, which is the second author from the paper, Dr. Raj Kumar, and he was actually on my thesis committee. So I actually asked him, I said, are you designed to actually for a system to actually handle deadlock free or what's that? He said, he looked at me, he said, yeah, we actually just designed the protocol. It's like a buy one, get one free. Does it actually work? That works. Okay, so let's actually look at these two problems and see how they avoid this one. So the first problem is about deadlock. So priority inheritance protocol, it actually helped the avoid or reduce the amount of blocking that you will have. But it still it's possible to have a deadlock. Just like two-phase locking, you could have deadlock as well. So this one, you have deadlock. And deadlock is particularly undesirable for real-time system. I mean, if you don't have a real time, that's fine. You have a deadlock, I can reset, I can try to break it, that's okay. But if the satellite is going to crash something, you better handle that immediately. So in real-time system, deadlock is really something they really want to reduce that probability to be zero. That's why deadlock is so important in this picture. The second thing, which is not so obvious, is that yes, I actually reduced the blocking time for the medium task to actually causing trouble for the higher priority task. But there is still a chance if you have a lot of medium priority tasks, you can still, oh, sorry, it's not a lot of medium priority tasks. If you still have a large number of mutual exclusion you want to get, and then there's a lots of lower priority, they actually get it, you can actually be blocked, accumulate. The example looks like this. So here is an example. I have n different tasks or n different threads. N1, tau 1 is the highest priority thread. It actually needs n different resources. It needs n different resources. And guess what? Each of the other thread, actually, sorry, I cheated, n-1 resources. It needs n-1 resources from R2 all the way to Rn. And the thing is that it just happened that there are n-1 thread, which is represent tau 2 to tau n. They actually each holding the resource once. So the accumulation will actually looks like this. So the highest priority, when they actually want to get into something, they realize they exactly get blocked once by tau 2 to tau n. So that is actually also something real-time system try to avoid. I said, well, I'm the highest priority task. I want to reduce the probability that I won't get blocked so many times, even though I actually need multiple mutual exclusion. So essentially, let me translate the direction about the requirement is that regardless how many mutual exclusion I need as a highest priority threat or higher priority threat, regardless how many, this could be 10 million, this could be 10, this could be n, or could be whatever number you pick. I want to be guaranteed I only get blocked once, one duration of the critical section. So that is actually quite interesting. I mean, wow, this essentially is independent of how many mutual exclusion you try to go in. And the worst case, you get blocked only once. That's exactly what priority ceiling protocol is going to do for us. Is now I'm going to introduce probably the most popular. I'm going to tell you two different protocol. One is called PCP, Priority Ceiling Protocol. One is called PCE, which is Priority Ceiling Emulation, which was not actually discussed in the paper, but I want to share that with you. I think that's probably the most practical priority ceiling emulation. So Priority Ceiling Protocol is essentially the most popular protocol to handle this situation. In the modern operating system kernel, they all have this priority ceiling feature already in the kernel, and there are system call features that you can actually do that. As long as you have fully preemptive kernel, you will need PCP. So what PCP is doing, it has three things that's actually trying to address. Number one, as I said, it will, regardless, okay, remember, regardless how many critical section you like to have. In the lifetime of this higher priority thread, it can at most get blocked by one duration of the critical section. Because I know critical section is going to be short, this is really, really desirable. So I can guarantee I will not be blocked like the way I described. That's number one. And the second term is that the deadlock will be prevented or avoided. Okay. Have you heard about the term called deadlock prevention? Have you heard about the term called deadlock avoidance? Well, in operating system, these two terms sound semantically similar. At least the result is similar, but it actually means different things, which I will talk about that, okay? It's important to know the difference. So in this case, priority ceiling protocol, the deadlock is avoided. I'll explain why I said deadlock is avoided, not prevented. Okay, deadlock is avoided. And the third thing is you don't need transitive inheritance. And not only you don't need transitive inheritance, but all the complexity of transitive inheritance is gone. It's partially because you only get blocked once. And the whole thing is actually happening. Okay, so that's the three things the priority ceiling protocol is going to accomplish. Number one, at most one block. Number two, deadlock free. Number three, no transitive inheritance. No transitive inheritance. Yeah, that's right. Okay, so I want to actually first tell you a little bit about difference between deadlock prevention and deadlock avoidance. So the way to actually say the difference is that deadlock prevention is that I'm a threat, that I actually go into the system. And I just basically follow whatever they told me to do. And there's no chance the deadlock is going to happen as long as every single thread follows the same procedure. So essentially, I'm just driving in Davis, and I follow certain traffic rule. And I don't really need anybody, I don't need to watch other people are doing. I just follow the rule. And then there is no collision in that case. It's called deadlock prevention. What is the example of deadlock prevention? For example, it's a traffic light. Traffic light is if a red light, you stop. Green light, you move. You don't worry about whether there is a car or not. And then you just do whatever you do, follow the procedure, nothing will happen. Okay, so that's basically deadlock prevention. And one of the very typical example about deadlock prevention in the Semaphore, the mutual exclusion, is what we call resource ordering. The term resource ordering means that everybody follow the same order to enter all possible mutual exclusion. So if I want to go for two semaphore, two mutual exclusion, one is a fork, one is a knife. So essentially we say you must first enter the knife mutual exclusion before you enter the fork, assuming that's the procedure. So if everybody actually pick up knife first before they pick up the fork, there's no way that you're going to have a deadlock. So essentially you don't care other people's status in their eating. As long as you follow something, then there is no deadlock possibility. Okay, so this is actually called deadlock prevention. Deadlock avoidance, on the other hand, is that when you're driving or when you're entering the semaphore, you actually need to pay attention to what other people are doing. So you actually need to see whether there's other thread might be doing certain thing. And so you try to avoid that because you see it's coming. That's why it's called deadlock avoidance. Okay, we're going to see priority ceiling protocol is actually a deadlock avoidance because it actually checks whether other threads are doing. On the other hand, PCE, which is the last one I'm going to tell you, is called priority ceiling emulation. Priority ceiling emulation is actually deadlock prevention. So depending on you're doing PCP or PCE, that you will see the difference. One is deadlock prevention, one is deadlock avoidance. Okay, all right. So let's first talk about PCP, priority ceiling protocol. How do I do that? Okay, so so the basic question when we try to understand mutex is the following. Is that when your program is reaching the point, it's reaching the point when you need to enter a mutex. So this maybe you want to pick up the knife. Okay, or pick up the fork, whatever. When you actually get to that point, whether you should actually take it. So with priority scheduling saying that, well, as long as this knife is there available, nobody wants it, I'm going to grab it. the basic without even priority inheritance protocol. Also, if you're doing priority inheritance, you realize that I'm the lowest priority task. But when I actually go there, if that knife is available, I'm actually going to grab it. As long as it's available, I'm going to grab it. So essentially, in both cases, you actually go in. So there is a risk, in fact, if you grab something, but the highest priority task is actually going to come in at a later point, like what we described, then essentially you're causing a enormous amount of the blocking because of that. So now what we want to do is that in priority sealing protocol, even if the semaphore is indeed available, you might not want to lock it. And we need to do some check. That's why I call it deadlock avoidance. You're actually going to see what other threads are doing. And if you do that, then we can guarantee all the property that we talk about that. But the issue is check on what? What kind of things we need to check? That's actually the trick about what PCP is helping us to develop. Okay, so we have to define a value called priority ceiling. So essentially, priority ceiling is a number that's assigned to every single mutual exclusion, every single mutex before the system start running. So in some sense, mutex you can think about is almost like a compiler concept. So when I actually want to compile the whole system, I want to decide what should be the value I should associate with the priority associated with the mutex. That's called priority ceiling. So let me actually tell you what priority ceiling is. Priority ceiling, the number that's assigned, is essentially the highest priority that's actually possible to access this mutex. So let me say that again. Sometimes I have to say 3 times for other people to understand. Maybe some of you can do better than me. So essentially, in my system, there are n different threads that might want to, they might not actually get in, but they might want to get into this mutex. Then the highest priority among all of them is my priority ceiling value, which priority ceiling basically is saying that it's impossible to have any thread with higher priority than the priority ceiling value wanting to get into this mutual exclusion. Okay, so that's called priority ceiling. All right, so essentially let me explain to you what this looks like. Is that the general rule is that if I actually, before I actually enter the mutex, this mutex I'm interested. So of course, this mutex is what? Is actually unlocked, right? Nobody's there. That's why if it's a lock, I'm out of a lock already. But assuming this mutex is actually available, then I'm actually going to check every single mutex is currently being locked. Okay, I have a 2 group of mutex. One group is available, one group is already being locked. So I'm actually going to check every single one that's being locked and look at their priority ceiling value. If my priority is not greater than the highest of those it's already locked, then I'm not going to enter the semaphore. Okay, let me repeat it. This is available, but here are the resources, or whatever. There is a few of them that are being locked, okay? And remember, there is a priority ceiling value associated with each of them. So I have my own priority. I want to go in here. It's very strange. I'm not actually looking at the priority ceiling of this one. I'm actually looking at priority ceiling of this guy, which I might not want. And the thing is that if my priority is not greater than this priority, I'm not going to grab this one. That's what it says, the priority ceiling. But let's actually go through the example. And then gradually you'll see, the first time I actually learn about this concept, it's actually quite not so intuitive. But priority sealing protocol is something which you actually start to, okay, let me tell you my learning process about this protocol. I try to come up with contradict example. I try to say, if I don't do that, I should be able to do that. I don't do that. And you try so many times, you realize that, okay, finally through the process, I actually learned that this is indeed necessary, almost optimal to actually be able to achieve what we want to achieve. Okay, so here is the picture. So I actually separate my semaphore into two different groups. One is locked, one is unlocked. Okay, one is locked, one is unlocked. So essentially, I am assuming I'm thread number 2, T2. I'm thread number 2. I actually want to get the second semaphore on the left. Okay, I want to go in. It's available. I should be able to get it. Okay, so if this is priority inheritance protocol, PIP. Sorry, you missed that because it was blocked by the Zoom. Thank you, Zoom, for blocking my slide and the important part of my slide. And if this is a priority inheritance protocol, you just grab it. Okay, you just grab it. Okay, so now let's actually look at this original picture. There are 4 mutants are being locked right now in the yellow box. Those are being locked. And the number that's actually on the semaphore is actually their priority ceiling. So the first one is our priority ceiling is 1, 4, 2, 4. Even though the threads that's currently holding it is actually much lower priority. So you can see that the priority number 9 is holding the first semaphore. That's actually priority ceiling value number 1. Okay, even a lower priority holding a higher priority ceiling mutex, I have to respect that and not to lock it. Okay, so that's essentially priority ceiling protocol is trying to do in this case, is that I'm sorry that there is a risk for doing that. I have to respect that. I actually don't want to do that. Okay, so I have to hire. That's good. Okay, let me ask your question again. What happens if this is 2? So I change. My priority is 2. T2 means my priority is 2. And what happens if there's no 1? There's just 2. 2, 4. The only difference between these 2 is that I'm actually getting a priority ceiling that's equivalent to my priority. Can I get in? No, I cannot. I can get in to help reduce the blocking, but if I get in, I'm actually going to cause deadlock potential. So it was designed such that, remember, I want to do deadlock free. So the thing is that if we are equal priority, we actually don't check on each other, we go in, then essentially deadlock might happen. And therefore, if I actually do it this way, strictly higher, not equal, higher and equal, it's a strictly higher, then essentially I have to wait until thread number 9 to release, to finish. I have to wait them to finish that, and then I can actually go in. Okay, that's the idea about how to do that. Okay. So this one, you cannot do that. Okay. Let's try to run through some example. Okay, I mean, this exercise, you can do it yourself. I'm not going to repeat it here, but I really think that you can actually read a paper or listen to what I said earlier and try to find counter example. I feel sometimes that's the best way to learn a concept, but I'm going to show you one example. Okay, before I actually show you the example, we're actually assuming we're using two-phase locking, meaning that all the lock is in one phase, all the unlock in another phase. In other words, the lock semaphore S1, S2, S3. If you lock S1, S2, S3, you must release S3, S2, S1 in that order. Okay, so two-phase locking is desirable to make sure we have serializability. All right, so that's one. Okay, so now I'm going to give you an example. So here, question? Okay, I'm going to go through this example. The first example I'm actually going to show you is that I have 4 different tasks. I have 4 different tasks. If you see the pink region, that means that is a local computation. Is basically not related, not guarded by Semaphore. And I have actually 2 different Semaphore in this picture. One is yellow, one is green. So I have a yellow semaphore, I have a green semaphore. So you can see that task number 1, he will need both semaphore. Task number 2 wants green, and task number 4 wants yellow. And task number 3 just needs nothing. Okay, just a local computation. And for the other 3, white, red, and blue, you will see that. Okay, red is essentially saying that it's blocking. Okay, so let's try to run the code. Of course, we're assuming single processor. There is a version you can extend it to multi-processor, parallel processing, which is still handle the priority ceiling issue.
So 1, 2, 3, 4 are priority.
Yes, yes. 1, 2, 3, 4, there is priority. Thank you for clarifying that. Okay, so let's see the first case. The first case is just regular scheduling without even priority inheritance protocol. So it will look like this. We probably already see this. So priority number 4, thread number 4 come in, grab the yellow, and then thread number 2, thread number 3, they both come in. And thread number 2 actually win because it has higher priority. So we actually grab the green. And then thread number 1 come in. When they come in, after he finished the local computation, the 2 pink. And then they realize it needs yellow. But the thing is that yellow is actually being grabbed by thread number 4, so it gets blocked. It gets blocked. Okay, now it's not ready, so it's basically 2, 3, 4. Of course, 2 will win. So 2 will finish the green and then finish the pink. And then 3 actually do that. And then finally 4 is going to finish the 3. As long as the yellow is available, now thread number 1 come back, it can finish. Okay, so that's basically a regular scheduling with mutex. Okay, and let's actually look at the number. The number I actually put 4 number here is 12, 6, 8, 17, means that the time each of the tasks spend to finish the whole thing. So for example, the first task is actually needs 12 units of time for it to finish. And then 6, 8, 17. Okay, so I just want to tell you that there is a 2 particular period that's actually very important. This 4 extra blocks. So there are 3 blocks over here. This is actually unavoidable because you actually allow somebody to come in. You have to wait until this yellow to finish. So this 3, I don't blame anybody. It has to be there. But this 4 is actually extra blocking. It's priority inversion. Because this is actually because you didn't use any of the priority inheritance idea, so you make your highest priority suffer. So it actually takes 12 units of time to finish. Okay, so now we're actually look at priority inheritance protocol. I call it basic priority inheritance protocol because it doesn't use the concept of priority ceiling. So you can see that from 12, I actually reduced to 9. Why 9? Because at the time I tried to enter yellow, at this time, now thread number 4 is going to win because thread number 4 now has the highest priority. So 1, 1, 1, and then 2 and 3 cannot come in to grab away the CPU. And now, okay, I just need to wait 3. And then basically the yellow, but then it lost to green again because why? Because I already blocked green over here. So totally you got blocked 1, 2, 3, 4 due to the mutex. So here you start to see the difference is that in fact the highest priority task get blocked or when I say highest priority, I really mean higher priority. The higher priority tasks get blocked 2 times by the lower priority task. Okay, in this case. So the time is 9, 12, 14, and 17. Okay, now I want you to guess by just looking at this picture, how short I can actually reduce this scenario from the highest pole. You know what? I'm sorry. You actually not seeing the most important. You see, I have this number here. It was blocked. Okay. So I want to move these things here. Can I actually move it and then still I can see this? Let's try my luck again. You still? Yeah, no, okay. You know what? I'm going to use this one because I want you to see the number. Okay, so just let you know, I will put the slide. So the basic one is 12, 6, 8, and 17. Means that task number 1 actually spent 12 units of time from the beginning until we finish. By using priority inheritance protocol, the basic one, I actually reduced from 12 to 9. So my question to you is that how much I can reduce that 9 to an even smaller number? I mean, I cannot make it shorter than 5 because it has to at least have 5. But at this example, how short do you think we can actually improve? For example, if I use priority ceiling protocol, what do you think how much time I need to spend on this one? 6, okay. We actually might not be able to go to 6, but we'll actually go to 6 eventually, but I'm actually going to show you a 7, which is with priority ceiling protocol is going to be 7. So now I actually want to see the full slide so you can see the whole thing. But let me do this. Let me move this a little bit down. It's all because I'm blaming Zoom for not giving me the right spot. Okay, now I'm happy. All right. All right. So let's actually see why is priority ceiling is going to help. Okay. So first, I'm actually going to remember when we do priority ceiling, we have to remember this 2 boxes, lock and unlock. We want to track what's already being locked, and then for us to decide whether we want to get in. So essentially, when the first one come in, when the thread number 4, when they come in, because there's nothing that's actually being locked. Therefore, 4 actually realized there's nothing being locked, so I'm free to lock the yellow. Okay, so it will enter the yellow. The trick is number 2. When the number 2 want to actually enter the green, okay, this is the blue part that's actually happened. What's the blue? What's my color? Oh, this is called ceiling-driven indirect blocking. Okay, ceiling-driven indirect blocking. So essentially, I actually cannot go in to actually lock it. I cannot go into lock it because why? Because why? Because the yellow is locked. When the yellow is locked, and the thing is that the priority ceiling of the yellow is what? Is 1. Okay, oh, it blocked 50% of my ceiling value. Okay, you can see that. That's the ceiling value. I put it on top of that. So essentially, it's because of the ceiling value, because my priority 2 is not strictly greater than 1. So I get blocked. So okay, when the blue gets blocked, guess what? There's another important trick, is that I'm actually going to pass my priority to 4. This is, so priority inheritance in priority ceiling protocol will do 2 situations. One is the blocking, one is the ceiling blocking as well. So essentially at this moment, the thread number 4, its priority get bumped up to 2. Because why? Because I'm actually blocking 2. I haven't blocked 1. I don't know whether one will come in, but I'm already blocking 2. So that's why I actually need to bump up my priority to 2. Okay, okay, this is a bit tricky. So therefore, I'm actually going to go through this, and then until the green come in, the highest priority come in, and it get blocked by me. When the red block me, my priority get bumped up to 1. Okay, so every single blocking, regardless if it's red or blue, it might bump up somebody else priority. And then basically I'm a 1, and then I done yellow. Well, this time the difference is because task number 2 never be able to grab green. So that's why now I can actually go to the green without blocking. And then I finish. So you can see that in this case, I actually be able to finish everything in 7 units of time instead of, you see, we're doing from 12 to 9 to 7. And the thing is that, let's actually check a few things. I cannot argue with this diagram about deadlock 3. We have to use different methods to do that. But this, you can see that I actually only get blocked once in my lifetime. So any of the tasks will only get blocked 1 duration of mutual exclusion by lower priority task. In this example, only the yellow. I avoided the green. Okay.
So,
Yeah.
does this mean that yellow and green also to be prioritized? Like in the top of the diagram, you check 1, 1.
This 1, 1 means the priority ceiling value. The 1, that is a static number. It will never change. Because I said in compiler time, I actually look at all your code to realize that the highest priority task can get into this yellow is priority number 1. So that's why I assign that value. That value will never change.
So why are we saying the yellow has highest priority than green? Like in second, whenever the second is trying to get a resource.
You say this one.
Yeah, second.
Right. Okay. Okay. So when I actually want to grab green, okay, and this is a blue, but I want to say before I become blue, how do I become blue? So let's actually use this as an example. So let me actually use this as an example. It's probably better. Okay. So in this case, that this one is actually yellow. This one is yellow. The priority ceiling is 1. It's actually currently being locked by thread number T4. So I want to enter green, assuming this is a thread number 2, right? It want to actually enter the green semaphore, but the yellow is actually already being locked, and the priority ceiling is 1. So the rule is saying that if my priority, what's my priority? My priority is 2. If the 2 is not higher strictly than whatever that ceiling value, then I won't be able to acquire any semaphore. This is essentially what we're saying. Any, even if it's available. I cannot actually access any semaphore. That's kind of, that's why I get blocked. Not because I have some resource contention with another lower priority or whatever threat. It's just simply because there is a potential risk for the higher priority task will come in to prevent me achieve what I want to achieve. That's why I'm actually going to just let the yellow go. So in some sense, okay, what you're asking is actually trigger another way for me to interpret priority ceiling protocol. In some sense, I actually sacrifice a medium priority protocol's chance to finish earlier by actually ask them to block once. But the good thing is that they won't get blocked more than once. They will only also get blocked once as well. So I kind of amortize that blocking, the chain blocking into a bunch of threads. Each of them probably get blocked once.
So the key word here is like put all lower priority one is using a resource to block all other.
Yes, yes. If a lower priority thread is acquiring a mutex, like in this case, that has a high ceiling value is going to block everybody in between, try to access any new text. That's what they try to do. But it has a nice property. It's actually deadlock free if you do it that way. So it's a little bit unintuitive, but that's the way priority ceiling protocol works. You have yeah.
How does the scheduler determine the priority ceiling value? It doesn't look forward to the lock operation. There's no, oh, this thread may lock this
Right.
or not.
Right. So, okay, that's a good question. So there are two ways to handle this question. The first way to handle is that assuming that it's a real-time system, it's an embedded system, it's very small. So I have all the code. So I can actually determine in advance. So that's why it's predictable about what it is. Okay, that's one thing. But in practice, in a more general computer, that I don't know what application you will be running, right? So essentially, the first time I used a priority ceiling kernel is SumOS 5.0. This is a long time ago when they introduced a real-time version of the Sun microsystem. Now it's Oracle. They actually implement a system call to allow me to set the priority ceiling value of every of the semaphore. So essentially, they push the responsibility to the user. So the user, when you actually want to run the program, you must know that what is the ceiling value you should set appropriately. If you set it wrong, the system will detect error as a signal saying, hey, you said this to be this, but now you're having this priority accessing this. So in practice, that's actually going to work that way. Yeah, it's not ideal, but that's the. You have a question?
So then, based on her, like, as a user, you have to set up the priority ceiling for both the yellow section.
Yeah, right. For every semaphore, you have to set.
That's where the second thread couldn't run the three parties because the yellow currently has a priority ceiling of one, which is higher than.
Right. Exactly. Yeah. So the priority ceiling value actually dominates all kinds of situation. Okay. That's good. I think most of you got it. Hopefully, we all have some concept about what's happening. Okay, we're having this situation, which is priority ceiling value is. Let me see, how much time do I have? I just want to make sure I'm not running all the time. Okay, I still have 6 minutes. I think that's enough for me to finish. So now remember, it's 7, right? It's actually, I reduced that to 7. Can we do better? One of you said, can we do 6? Yes, there is a way to do 6. So to do 6, we actually run a protocol called priority ceiling emulation. So what is a priority ceiling emulation? It's actually very simple. The way it works is that if I actually enter a semaphore and nobody wants anything, I actually enter that semaphore. At the time I enter the semaphore, I'm actually change my priority regardless to the priority ceiling value. Okay, so you can see that right now, as long as I actually enter the yellow, my priority become 1. And then I'm just finish everything, and then now you're doing regular schedule like this. This is called priority ceiling emulation. And in this diagram, you can see that this is not always the case, okay? It's not guaranteed, but in this particular case, it's actually reduced to 6. But the advantage of priority ceiling emulation, the best advantage is so simple. It actually has all the property that we want to accomplish. Deadlock free, no transitive blocking, and any priority can only block once. And most likely is going to be blocked by the blue, which means that it's a ceiling induced blocking, not the resource contention. And another thing nice about priority ceiling emulation, the kernel implementation is a lot simpler. I actually don't need to track, don't need to inherit. I just grab the priority when I enter the ceiling value. And if you look at this, it reduces a lot of what we call context switch. If you look at this, what do I mean by context switch? From here, I switch to 2. From here, I switch to this. And then I switch to over here. You see how many context switching I'm going to have. With some of the system, I really want to reduce that. But with priority ceiling emulation, I'm just actually taking the priority or priority ceiling when I have it, and until I actually release the semaphore, and actually accomplish the result. And also, on top of that, now I go back to my previous question, is what's the difference between deadlock avoidance and deadlock prevention? Priority ceiling protocol is deadlock avoidance because I need to check the yellow box and the green box, what's being locked. Over here, I don't check. I just basically use whatever priority I have and just do it. So this has become a priority prevention case. Okay, this is very nice. All right. So I want to just spend the last like 3 minutes to discuss one thing. Let me actually just summarize. I'm going to ask you one thing. There is a whole thing about analyze. Why is deadlock free? I don't have time to do that, but you have to believe me, it works that way. Okay, if you find a way that the protocol can actually cause deadlock, you will be famous. Okay, because a lot of systems need to redesign. All right, so I want to actually tell you this fourth thing I introduced: priority inversion, basic priority inheritance, priority ceiling protocol, and priority ceiling emulation. I want you to ask one question. What do you think is the true difference in terms of the execution between priority ceiling and priority ceiling emulation? What do you think is the difference between these two? What do you think when I probably is really new to you, because you just learned all this concept. But what do you think the impact on scheduling between emulation and priority ceiling protocol?
It might be easier in emulation because there is no context switching activity.
Right. That's one of the, it's a simpler, right? The simpler. But what's the, let me ask a question different. What's the disadvantage of using priority ceiling emulation? I guess that's I should ask. What's the disadvantage or some kind of negative impact to the priority ceiling emulation? Go ahead.
Maybe waiting for a longer period of time.
The intermediate. Well, the intermediate task, if they, what kind of intermediate task? Let me actually ask you. Okay, you're hitting the point, but I want to be clarify what you mean by that. So I have, let me use this picture. I have two intermediate tasks. One is task number 2 and task number 3, right? Does priority ceiling emulation hurt more for task number 2 or task number 3?
Number 2.
I argue number 2 is actually the same. It's treated as similar between priority ceiling emulation and priority ceiling protocol, because they both need to be blocked for the time, the yellow to be released anyway. So there's but the truly one that's being hurt is actually this one, the task number 3. It doesn't have doesn't need any resources. It doesn't need any semaphore. So that's the true disadvantage of priority stealing emulation. If we have only 3 and 4, if we only have 3 and 4, and the thing is that with priority stealing emulation, I actually will immediately have a 1, 1, 1, 1. I actually will delay your time by 3. So take a look at this. Number 3 is a 14 over here. It takes 14. Is this still 14? Sorry. Yeah, it's still 14 for priority stealing. But this 14 will reduce by 3 or 4 if thread number 1 and thread number 2 never come in. So this is always assume the picture they come in. But if they don't come in, then 3 is actually going to hurt a little bit with priority stealing emulation. That's the only disadvantage of priority stealing emulation. Otherwise, it's actually doing very well. Very simple, guaranteed the same property, and it do what it's supposed to do. Yeah. Okay, so I think I'm going to finish here. This is basically, this is the lecture about your second midterm. Yeah, you have a question?
So in that case, if one and two don't have to properly set the student value to make sure.
Well, when I say 1 and 2 not coming, I'd say they have a potential to come in, but it's just 3 and 4 when they run, they don't come in. But so therefore the ceiling has to be 1 because we don't know whether 1 will come in or not. Yeah. So that's always some kind of unpredictability there. Yeah. But overall, the important thing is those strong properties are being preserved. That's actually very important. Okay. Any question from remote? Yes, we have office hour today at 4:10. All right, just to let you know, we have office hour at 4:10.